high-performance computing of basins of attraction for large-scale systems. So, Stefano, go ahead.
Thank you, Mohamed. Okay, I'm going to talk about basin of attraction for large-scale systems. First of all, let me show the outline. I will introduce the topic, and then I will discuss a little bit the algorithm, but skipping the technical details. Of course, there are a lot of technical details, and then I will show some results, and I will end with conclusion. Well, nowadays it is well known and realized that stability analysis is no longer sufficient for understanding some real behavior of system, especially when you get close to bifurcation points. You have to be aware that even if the solution is Lyapunov stable, the basin of attraction could be so small that in real world you can have imperfection, small imperfection, but not infinitesimal imperfection, in such a way that you can get out from this small basin of attraction, and practically your solution is unstable, even if you are believing that you are believing that it is stable, and theoretically it is Lyapunov stable. So this is the key point that Michael Thompson developed in the 80s, and then we are, together with Professor Orrega and other collaborators, Mohamed Younis, Paolo Gonzalez, we are trying to keep out and to develop these issues, which we name dynamical integrity. So dynamical integrity basically is related to the study of basin of attraction. And basically we have to be sure that the basin of attraction is large and compact enough in such a way that you can use that solution safely in real application. That's the point. And of course, the key point is to determine basin of attraction, because all the studies is based on the analysis of basin of attraction. So you need basin of attraction. Basin of attraction, I will tell you in a while the right definition, the technical or the theoretical definition, but basically are the subset of state space of initial condition leading to certain attractor, for example. So you start from here, you go to this attractor, start from here, go to this attractor. All these initial conditions are the basin of attraction, and they should be large enough. Well, building basin of attraction is a very, very difficult task. If you are in low-dimensional systems, this is easy. There are some tools, some freeware software, it is easy. If you go to large dimensional system, and when I say large, I mean over 4-dimensional systems. So it's not huge, but larger than 2, let's say. The computational issues become very, very, very important, and sometimes you are forced to stop because your machine does not reach the problem. So we are faced with this problem of building basin of attraction for large dimensional systems, and this is exactly what we want to do. And first of all, let me say that this is basically a work in progress. Okay, so we are just started to approach these issues, and the point we try to develop is to use parallel computing, because we realize that with serial computing we are at the bottom of the computer possibilities. So we have to change the paradigm. We have to move to parallel computing and try to exploit the parallel computing capabilities of computers, try to go ahead in this direction. So that's basically our motivation. So this is what basically I said. Here is the definition, let's say the mathematical definition of system of initial value. Basically, it is initial value problems, and the mechanics is, of course, here. Of course, I am a mathematician. I'm an engineering, sorry, and I come from engineering department. I'm interested in engineering systems, but these issues also for any mathematical system. Also from other fields, not only engineering, maybe biology, economics, and so on and so forth. So the systems are always written in this way. Of course, this can be large dimensional systems, and could be. And the spatial dimension could be as large as you wish. These are the initial conditions for a given initial time. And this is the evolution function, which basically satisfies the equation of motion, just technicalities from a mathematical point of view. And the here is the right definition of a basin of attraction. Basically, is you start from initial condition, run your system, and end up on an attractor, and then change initial condition, run again, and so on and so forth. And all the initial conditions leading to the same attractor are the basin of attraction. Basically, they are the the union of the evolution function measured backward in time, basically, starting from an attractive set. And the point is that basin of attraction consists of all initial conditions. Mathematically speaking, it's all initial conditions. Of course, all initial conditions is impossible from computational point of view. You have to discretize. So we have to consider also this point. Not only many dimensions, not only many dimensions of the system is in the previous slide, but also many starting points. So all of them introduce complication, introduce numerical effort, numerical demanding problems. So all of them have to be considered carefully. And here, what it is commonly done, the phase, first of all, you choose a window of the phase space, because you cannot, also the phase space could be infinite, and of course, you cannot consider the infinite phase space. You have to choose a windows. Here, I represent only a two-dimensional windows, but of course, in large dimensional system, you have to choose an hypercube, and you say, I want to study what happens in that hypercube. I want to determine the basin of attraction in that hypercube. And then you discretize your hypercube at a lot of cells reported here, and basically you consider as a reference point of this cell is centroid, but it is not really necessary. You can have a different approach. This is just the technicalities. And basically, you discretize your phase space. You discretize your phase space, and you will consider the initial condition only this one, the centroid of the other one, the centroid of the other one, and so on and so forth. So, in order to have a good resolution, the set of the initial conditions to be investigated need to be very large. This is the first point I told you before. And these increase complexity, increase computational efforts, as well as the high dimensionality of the system, of course. And the second motivation for our work is that, what I said at the beginning, that we are moving to, let's say, giving up about the single core computation, and we are moving to the multicore era, multicore computational era. And so you need to exploit these computational capabilities to improve our capability of determining basin of attraction. So we present a new algorithm which tries to exploit this multicore behavior of a modern computer, and we focus in this work, but we are working in a different direction as well, on cell mapping method. And cell mapping method basically is useful, works for periodic system, because you need the periodicity in such a way that you can build your map according to a Poincare section. But we can do also, we have done, not reported here, but we have done software and algorithm for non-periodic system using different kind of algorithms. But we focus only on this one. And basically, we build up a map of the phase space, built on a stroboscopic Poincare sections. Okay, so here the algorithm, and the proposed algorithm determines the multidimensional basin of attraction for n-dimensional system. And the key point is that we do not start from a given two-dimensional section. Maybe you remember the first day Valeria Settimi showed the construction of basin of attraction for five-dimensional system, but actually she starts from a Poincare section. Not Poincare, sorry, for a two-dimensional section, starting from every point on that. We want to build the basin of attraction of the whole phase space, not only a section at the beginning. So we determine all the basin of attraction. Of course, from drawing point of view, we'll represent only b-dimensional section, but we determine the whole basin of attraction. That's the really difficult and demanding point. And this permits to have different sections. In such a way, you can have different visualization, you can have different computation, you can have different feeling of what happened in different sections of your large dimensional basis of attraction. And yes, this is what I said. Okay, what we do. First, having defined the given window of interest, which is named domain here, we enlarge it a little bit because we want to consider also the solution getting out from this domain. It may happen, especially if you are involved with escape system. For example, MEMS, you have pull-in, or cubic nonlinearity with a negative cubic term, you have an attractor infinite. So you need to take care also what happens outside your given window. And so we enlarge a little bit the domain and consider this as the escaping attractor in some sense. So then from this is algorithmic point of view, we decide to save all the data according to our rolling procedure. I mean, we put all the data in a sequential file, basically, in such a way that we have easy management from a memory point of view. And the key point, I'm not an expert in let's say, in software, but my co-author is a very good one. And he told me that the key point is this message pass interface, because you have to pass information between different cores. That's the, let's say, the bottleneck, because every core can do a very good job, but it cannot work alone. You have to exchange information with the other cores, and this is really the bottleneck. And we will see how we try to address this point. So here are technicalities. We start with initialization. We check the coherence of the data, reallocation routine, but this is just technicalities. And what is really important is how we exchange information, in this case before. You see in this schematic picture, there are several cores with perform numerical integration. Basically, the idea is that each core starts from a given initial condition, and in parallel, each core integrates the systems. And you need another course taking care of the memory to store the data, basically. So some cores integrate, some other cores store the data. And they have to communicate between each other. And that's the memory source, or the sharing data between those, which is this master control project, which is really the most important point in developing the algorithm. And yes, this is what I said, some elaboration course, basically numerical integration and memory managers, and cell-to-cell mapping algorithm. Okay, these are technicalities. And let me show you how we decide to manage these issues. Basically, there are two different approaches. The first approach is that each course goes by himself, and at the end of the integration, we compare the results. They do not communicate during the integration, only at the end. So all of them start, at the end, they compare with each other. This is the second approach, sorry. And another one instead is they communicate in real time. What does it mean? It means that when one core finds a new attractor, it immediately advises the other core that the new attractor exists. So please stop, store in your data that there is a new attractor, and consider this. So these, of course, require much more exchanging of information. And as we will see, depending on the type of the problem, this approach can be convenient, and this one can be less convenient, of the opposites. Basically because the exchanging of information is a slow process. So it's much slower than the integration. So sometimes, if it is better to wait at the end and exchange information just at the end. Try to, let's say, I will tell you in the next slide, because I start with this one. What we do, every core go ahead, and just at the end, we call it coherence stencil. We check the attractor of every core, and we say, okay, this attractor is exactly the same that the other core found, and so they are the Vogt attractor. And so we share the basin of attraction of this attractor, just at the end of the integration. And this is relatively convenient from system where you have long attraction period. Basically for system where you have not periodicity, basically. This is the advantage of this technique. And you see, these are the rough data, and when you mix with the different core, you get the good result. Okay, the second approach instead, as I told you, is the real-time synchronization between the computing nodes, which means basically, as I told you before, that every time a new attractor is found, stop it, inform the others, and restart again. Not again, restart from that point, sorry, not again, restart from that point. And here are how to write the code in this multi-core system, just technicalities, of course. And here are our example. Actually, it's not multidimensional, but it is very, very precise. So basically, it is equivalent to a multidimensional system, because what is important is the dimension. And you see basic results are reported here. If you do the basic, if you build this basin of attraction with, where is 10 power 6 cells, so which is very, very fine mesh, with classical serial computer, you need 250 seconds and 159 seconds if you have a good CPU clock. But if you use cores, and we use 128 cores, you need only 39 seconds. Please consider that this system, we do this in a computational center here in Italy, but this number of cores is not huge. Basically, it consists in 4 PC, so it's not a huge number of cores. We can have much more than this in the real application. Just with 4, not regular, good, but regular PC, you can reduce the computational time of 300%. And please remember that 20 years ago, when I started my work on basin of attraction, to build this basin of attraction, we need 3 days, maybe, 3 days. 3 days with former computer, very slow, running, 3 days running night and day. So now 39 seconds for me is a dream in some sense. So I'm very happy with this result, because, you know, there are much more possibilities, of course. To go up to 1,000 cores is nowadays very, very easy, which means 3 seconds for a huge system. So this means that we are in the right directions. And as I told you before, the key point is the balance between the cores taking care of integration and the cores taking care of the memory and the passage of information. So this is the key point. So you have to balance. This is, in some sense, a drawback, because this means that you have to know your system. There is no a priori answer. Sometimes it's better to have a lot of cores taking care of the integration and few taking care of the memory, and the other side could be the opposite. So you have to do some preliminary, let's say, investigation, and then this is what we have done. We basically consider the number of cores and the percentage of the memory cores. For example, here very few, and here a lot of number of cores. And we record the computing time, and we found basically the best of the optimal division of cores, basically. And it is reported here for, you see, 60 million of cells, 60 million of cells, which means 500 by 500 by 200 cells in our phase space. And if we increase this number, you see the good computational area shift a little bit. So this is what I said. You have to know where you want to go. You have to do some preliminary study in such a way you improve your computation. And you see the gain is very important because you reduce of one, for example, from this bed area, you reduce of 1/3 the computational time. So you really need this. And even with close to 1 billion of initial conditions, you can have the basin of attraction in 200 seconds, which is very, very, very good. So basically, this is what I've done, what we have done, sorry. And as I told you, this is still work in progress. We are still developing the algorithm. And of course, next step is to apply this algorithm to real system, to very complicated system, to build the dynamical integrity and so on and so forth. So the results show an enormous potential of these algorithms, and the computation must be instructed properly in order to obtain the best performances that you did before. This is a drawback, but it is necessary. So you need to do some optimization before, and the proposed two-step algorithm has been presented with the description of cross-section generator that perform multiple 2 degrees of freedom plots. And let me say that we believe that the serial software computing basically is ended. So we enter in a new era of computation, the multicore era, and we have to give up about serial computation. Thank you for your attention.
Thank you for the presentation. Questions? Yeah.
Stefano, thank you very much. Very vigorous presentation on computing science almost. The brute force will never replace thinking. I think we cannot. So we can do faster. Do you see computations of that sort that you apply to the basins before for the design or for control?
No, my idea is for the design, my idea. I hope that we will be able to have some result from the design.
So we know design process is basically is a lengthy one. You start with, let's say,
rough ideas,
and you have, so my question is, it is very useful. If I can check dynamics and check it very quickly, it allows me to basically play around. The question I have, do you think there is a scope to rethink how the basins are computed? Because the brute force, you can speed it up, but of course we will not get. So what I understand, once you locate the attractor, you should be able to use the topological features of the behavior to actually get there.
Yeah, I believe that one basin of attraction must be computed by brute force. What you can do, when you change the parameter, you can try to exploit the information of the previous slide, if you wish, for building the next slide. But the first one should be built by brute force. There is no issues. Then you can focus on the boundary, see how the boundary and how the attractor change by varying the parameters, and you can save time and computing efforts.
Stefano, cannot we locate the equilibrium points and then locate the unstable manifolds?
Yeah.
Suppose we get the unstable manifolds. Won't it give you the basin of attraction bounded for you so that there will be less computational time and effort and so on? Because the unstable manifolds are separating these basins of attraction.
Thank you for giving the possibility to reply. The answer is yes, if you are sure that you will find every saddle playing a role. Unfortunately, this is not always the case, because at least up to my experience, there are many minor attractors with very, let's say, small basin attraction which play a very important role in the overall organization. And if you do not pay a lot of attention to look around for all saddles and all unstable manifold, you can miss some things. So in principle, yes, but practically you can risk to miss something. For sure, if you to consider the most important, you have an overall picture, but you are not sure 100% that this is the whole picture. And since dynamical integrity is related to the basin magnitude, if you have very small basin attraction inside the larger one, you destroy the integrity. So this could be very dangerous, in principle.
This is what, will be having more attractors in the system.
Yeah.
But if you have more attractors in the system, then it becomes, can't we again find where are the equilibria and the unstable manifolds within that?
Yeah, but
because instead of looking over so many initial conditions and
yeah, but I understand that, of course, you want to. Oh, okay. First of all, if you have only one attractor, basin no attraction does not mean anything. Of course. Yeah, of course. So, of course, I understand that, and I agree with you that you wish to work in a regime with very few attractors. That's your goal. I agree with you. But sometimes, and this happened to me, in spite of your wishes, the devil is behind your walls and put a lot of minor attractors, unwanted, but they are there. And you cannot forget it. This is, sorry.
This is what I heard, that you should run that in two basically phases. The first phase is to see, let's say, nonlinear dynamic structure of the system, and that could be done either by path following or something, so you have understanding what it is. And once you have done that phase, then you probably can speed it up quite drastically, your brute force computation.
I agree.
So we continue discussion now. This is time to go for the break. Thank you again, Stefano.